Hi guys! This video is about the 5 applications of dot product we'll be discussing in our course. The first application is to determine lengths and vectors, or excuse me, not vectors, and angles. And I'll show you a few examples of that in just a minute. The second application is to determine if two vectors are orthogonal to each other. Remember, u and v are orthogonal if they meet at a 90-degree angle. Sometimes we also say that they're perpendicular or that they're normal. Usually we use the word orthogonal when we're referring to vectors. Another thing that dot products can do for us is that they can allow us to find projections of one vector onto another vector. And I'll tell you what that is more in a little bit. We can also find the work done by a force. Remember, force is a vector. In moving an object some displacement d. And lastly, and this is not for this standard but for the next standard, we're going to use dot product to calculate the distance, the shortest distance between a plane and a point that's not on the plane. Okay, so we're going to focus on this one this time. And actually you should notice that if I'm determining lengths or angles, I'm determining if two vectors are orthogonal to each other, that's determining if there's a 90-degree angle between them. So that's actually a special case of number 1. And when we find the projection of one vector onto another vector, we're often interested in its length. So this example of projection is just length plus making it a vector by multiplying by the appropriate unit vector. So 2 and 3 are really just special cases of 1. But let's look at number 1, and let's look at a simple example. Let's say you're given two vectors, u equals the vector with components 1, 1, 1. And v equals the vector with components 1, 2, negative 1, and someone asks you to find the angle between the two vectors. Well, it's pretty easy. Knowing what we know about the geometric definition of the dot product, the dot product of u and v is just the length of u times the length of v times the cosine of the angle between them. Now, even if I drew these two vectors in three-dimensional space, it would be hard to infer from a two-dimensional picture, from a certain perspective, what that angle is between the two vectors. But using this formula, I can find theta. If I've got component form of u and v, I can take their dot product. Using the algebraic definition, we'll just multiply component by component and add. Then I can find the length of u and the length of v, and then the only unknown in that equation is theta. So let's do that. I'm going to compute this and this and this. So one piece at a time. U dot v comes from multiplying component by component and then adding the result together. So we just get 2. The length of u, remember how we find that? We take the components, you square them and add them and take the square root. We get square root of 3 for the length of u. Length of v, do the same thing. Take the components, square them and add them and take the square root. Now I can substitute these guys in over here and then just solve for theta. U dot v is 2, and that's equal to the length of u times the length of v times the cosine of the angle between them. Now if I'm getting theta by itself, I can just multiply these two guys You can simplify that if you want to, but you don't have to. Divide by the square root of 18. I have a desire to simplify that because I'm a math teacher. It's absolutely not necessary. But I'm like, oh, I really want to do that. Oh, that makes me feel much better. Okay, so cosine of theta has to equal this. And if I'm trying to get theta by itself, I take the inverse cosine of both sides. Now remember, inverse cosine is only going to give you an angle between 0 and 180, 0 and 180 degrees, or 0 and pi radians, and that's actually just what you want. Whenever we're looking at the angle between two vectors, we're always talking about that angle between 0 and 180. So if this is u and this is v, theta is always that angle. It's not the other one. If v was actually going this way, well, then theta would be that one. It's always going to be the smaller one. So the inverse cosine will always give you the right answer. My calculator is in degree mode. Just going to use that here. Got shift inverse cosine of 2 divided by, open parentheses for the denominator, 3 times the square root of 2. Close parentheses for the denominator, close parentheses for the inverse cosine. And it turns out to be about 61.9 degrees. All right. So that's one thing that dot product can do for us. It basically allows us to determine that angle. It's exactly what it does, not basically. It allows us to determine that angle if we have the component form, because this can be calculated, and this can be calculated, and this can be calculated. Now, it turns out we don't even have to do this much work if we're just interested in figuring out whether the angle between the two vectors is acute, obtuse, or a right angle. So just let's look at that formula again. Here's our geometric definition of the dot product. Now we know that the length of u and the length of v are always going to be non-negative. The only time they're 0 is if one of those is the 0 vector, and then this is all very simple. If it's the 0 vector, we're going to get 0 out as our scalars, so there's not really much going on here. But if one of these is not the 0 vector, if both of these are non-zero, that's a positive number and a positive number. So the sign, S-I-G-N sign, of the dot product is completely determined by cosine of theta. It's probably been a while since trig, but you'll remember, I hope, that cosine of theta is positive when x is positive. So it's going to be positive over here. Then cosine of theta is 0 on the y-axis, and then cosine of theta is negative over here. Remember, cosine is positive when x is positive, cosine is negative when x is negative. And we're always going to be in one of these two quadrants. There's always an orientation where we can draw the vectors, so one of them's over here and the other one's going to be over here or over here or over here. And that's going to be good enough to tell us whether the angle between the two vectors is acute, obtuse, or a right angle. So let's do the two very special cases first. Okay, so let's say u points this way, and v also points that way. Well, then the angle between the two vectors is 0. 0 radians, 0 degrees, it doesn't matter. So the dot product is going to give you the length of u times the length of v times the cosine of 0. You remember, cosine of 0 is just 1. So this is going to give us the length of u times the length of v. So that's the largest the dot product could possibly be. It's just the product of the two lengths. And that only happens if these guys are going in the exact same direction. Now we might have, at the other extreme, u going this way and v going in the complete opposite direction from that. Maybe that's my v. In that case, the angle between them is 180 degrees, or pi radians. So in that case, u dotted with v is the length of u times the length of v times the cosine of 180, or cosine of pi radians. Well, that's -1, guys, remember? So what we get there is -1 times the magnitude of u times the magnitude of v. Now remember, the maximum value of cosine is 1 and the minimum value of cosine is -1. So this is the least that our dot product could be. You multiply the lengths and then you multiply by -1. So all those other values for dot product, they're always going to be somewhere in between here. If this was, say, 2 units long and that was 3 units long, I don't know which way they're pointing. I know that the values of the dot product are going to be between -6 and 6. They'd be -6 and if they're in opposite directions, and +6 if they're pointing in the same direction. Now, so those are our special cases. Now, what things get a little bit more interesting if we're here or here or here. Now let's say you have an acute angle. Maybe this is u and this is v. Well, remember from our picture, if I draw that in the xy plane, this is over here where x is positive. So that means cosine of theta is positive. And if cosine of theta is positive, that means u dot v is positive, because u dot v is the length of u times the length of v, both positive, times the cosine of the angle between them. If this is positive and these two guys are positive, the dot product is positive. So if theta is acute, then we're guaranteed that u dot v is positive. And this is cool too. If you just compute u dot v, you get a positive number. Now you know that theta is acute. That's only if, let's say, if you get a positive number and u dot v is not the length of u times the length of v. So if it's positive and it's not the maximum possible, so that they're both pointing in exactly the same direction, you can say they're kind of pointing in the same direction. Like this one's pointing over here, and this one's got a component that's parallel to that. It's sort of pointing that way. So u dot v is positive when theta is acute. Now if theta is 90 degrees, if this is u and this is v, well, cosine of 90, cosine of pi over 2 radians, remember that's 0. So if you get a dot product that's 0, you immediately know that u is perpendicular to v, or u is orthogonal to v, or you know that theta is 90 degrees, or theta is pi over 2 radians, same thing. Or if you know that that angle is pi over 2 radians, you immediately know that visually they're perpendicular to each other, or orthogonal to each other, and the dot product is 0. Now the final case is if u is over here, and let's say v is over here. There's my angle theta. Well, we know in quadrant 1, cosine is positive. In quadrant 2, cosine is negative. So this time, u dot v is the length of u times length of v times cosine of theta. And this time, this is going to be a negative number. And since that's a negative number, that means our dot product is negative. So u dot v is negative whenever theta is obtuse. And u dot v is not equal to the negative length of u times the length of v. If it's the negative length of u times negative length of v, they're pointing in opposite directions, but that theta is obtuse. If it's negative, it is sort of pointing that way. We can say it's like almost pointing in the opposite direction. Not technically, not the way we've talked about it. But notice that the x component of this one is negative, and this one is all positive in the x component. like their x components are in opposite directions here. Here their x components are in the same direction. So these are like roughly the same direction. These are roughly the opposite direction, but they're not exactly opposite, like this one and this one, or they're not exactly the same direction, like this one and the positive x-axis, that one, or hi-hat, or something like that. Okay. Now with that in mind, you can use this idea to determine if a triangle with given vertices is an acute triangle, an obtuse triangle, or a right triangle. Now again, if I've got 3 points in three-dimensional space, I might not know what these look like. And even if I draw on a 2D piece of paper the points A, B, and C, and then try to draw a triangle connecting them, I'm not 100% sure what it looks like because of the perspective of my 2D drawing and the angle that I'm looking at it from. So the best we can do is a cartoon. I'm going to draw a point A here, and a B here, and a C here. So I'll call that A, that B, and that C. Now that forms a triangle. Now if I want to know whether this angle at point A is acute or obtuse, I need to find the vector from A to B and the vector from A to C, and then determine if that dot product is positive, negative, or 0. So let's do that. Let's find the vector from A to B. Remember how we do that. Take the terminal points coordinates and subtract the initial points coordinates. So we have -1, 5, 8, subtract 2, -7, and 3, and we get -3, 12, and 5. Now I want to look at AC. Notice they both start at the same point. That's important. In order to find the angle between them, they have to have the same initial point. So that's my angle A. I'm going to label the point A and the angle with the same letter. So I start with my terminal point, start with 4, 6, -1, and subtract the coordinates of my initial point, -2, -7, and 3. So I get, so I'm subtracting 2, subtracting -7, and subtracting 3. Yeah, that's what I wanted to do. So I get 2, 13, and -4. Now if I want to determine whether this angle at A is acute, obtuse, or right, I just take the dot product of these two vectors. That's easy enough. Remember how we do dot product? You multiply component by component. So I've got -3, 2, plus 12 times 13, plus 5 times -4. What's that? Well, it's -6 plus, what's 12 times 13? Looks like 156, and then I'm subtracting 20. Well, I've got 156 minus 20 is 136, 136 minus 6 is 130. It's positive, so what does that tell you? From down here, dot product's positive, that means the angle is acute. Now that does not mean we have an acute triangle. Right triangles have one right angle and two acute angles. Acute triangles have 3 acute angles. An obtuse triangle has 2 acute angles and an obtuse angle. So that means there's a lot more work to do. I need to find the angle at B as well. It's actually not that bad. The angle, to find the angle at B, I need the vectors BA and BC. BA is just the opposite of AB. So I'm going to take this guy, multiply it by -1, so I get 3, -12, and -5. I'm going to dot that with BC. Take the terminal point at 4, 6, -1, and subtract the initial point. So I'm subtracting -1, subtracting 5, and subtracting 8. So we get 5, 1, -9, and then take the dot product of those two guys. BA dotted with BC, that's 3 times 5, oops, plus -12 times 1, plus -5 times -9. We've got 15 minus 12 plus 45. So that's 3 plus 45 is 48. 48 is positive, so angle B is acute. All right, so I guess we do have to check all three because the first two are acute. If either one of those was right or obtuse, we would get to stop. But now we've got to do at the angle at C. So we need AC or CA and BC, or CB, excuse me. Now CA is just the opposite of AC. So just take this one, multiply it by -1. Then CB is the opposite of BC. Take that guy, multiply it by -1. Then dot them. So I've got -2 times -5 is 10, plus -13 times -1 is 13, plus 4 times 9. I'm not even going to do the arithmetic. Positive plus positive plus positive is positive. So angle C is acute. All three angles are acute, so it must mean the triangle ABC is an acute triangle. Okay, so let's go back to this. We have just taken care of this first one, finding lengths and angles. We really more focused on the angles here. We said if the dot product is 0, the two vectors are perpendicular to each other or orthogonal to each other. So we've taken care of these first two. I'm going to talk about projections in a different video. Just one note about terminology. You might say, Miss Townsend, you're using the word orthogonal and perpendicular sort of interchangeably, and I am. Orthogonal, perpendicular, and normal all basically mean the same thing, but we tend to use the words in different contexts. All three of these words mean that the two objects that we're talking about, if they're orthogonal to each other, perpendicular to each other, or normal to each other, means that they meet at right angles. Now, we tend to use orthogonal for vectors. We say that vectors are orthogonal to each other. We say that lines or planes, or surfaces even, are perpendicular to each other. And when we say two things are normal, usually we're talking about a vector and something else. So a vector is normal to a surface, or a vector is normal to a line, or a plane being a specific type of surface. But anytime you hear orthogonal, perpendicular, or normal, just know that that means the two vectors meet at 90-degree angles, the two planes or lines meet at 90-degree angles, or that we've got some surface or some line and we've got another vector that's perpendicular to that. That's what we mean. That's what we mean, when we use the word normal.